Welcome to This Explainer. Today we are taking a deep dive into the blueprint of literally the most advanced ship never built, the SS Lorentz Horizon. If you're fascinated by the absolute cutting edge of naval architecture, biomimicry, and solid-state engineering, you are going to love this. We're looking at a conceptual vessel that completely rewrites the rules on how massive ships move, operate, and survive in the most hostile environments on Earth. $147 million. Now that massive number right there is the complete turnkey financial commitment to bring this incredible ship to life. But it's important to understand how that actually breaks down. It's a $136 million hardware build, with the remaining $11 million allocated specifically for its first-year operational deployment and crew provisioning. For a ship of this scale and capability, that price tag is actually incredibly disruptive, and we're going to see exactly why.
To wrap our heads around this dense engineering document, we're going to take an anatomy tour. We'll start by meeting the Lorentz Horizon, dive down into its bio-grown hull, check out the solid-state MHD propulsion, look up at the towers, tech, and drones, and finally, break down the fleet's economic edge.
All right, Section 1, meet the Lorentz Horizon, the ultimate off-grid relief node.
So let's start with the big picture. What exactly is this thing? Well, it's a 380-foot, 4,200-ton displacement vessel. But its mission is really what sets it apart. It's designed specifically as the ultimate off-grid disaster relief node. The whole goal is to establish survival nodes in under 48 hours. To pull that off, it carries an automated hangar that supports 20 VTOL drones. Inside, you've got a biofoundry apothecary lab that can literally produce cloned medicinal manifests right on site. Plus, it tows a daughter node barge packed with 20 crated communications towers and 10 e-cycles. It essentially brings a fully functioning, high-tech piece of civilization straight into a disaster zone. Moving down to the bottom of the ship, Section 2, the bio-grown hull, living armor and hydrodynamic slip. Okay, this is where the architecture gets straight-up sci-fi, because the hull isn't just manufactured, it's bio-grown. Initially, early drafts planned for a hovercraft-style design with rubber skirts, but they totally scrapped that. The risk of tearing those skirts on coastal wreckage was just way too high. Instead, they went with a fully submerged 380-foot solid bio-grown mycelium shell. That means zero moving mechanical lift parts. And because it's a mycelium composite, it's quite literally a self-healing living skin, topped off with a super hydrophobic chitin coating. Now you might be wondering, how does a 4,200-ton organic hull move fast? It uses an active microbubble air lubrication system. First, micro-perforated vents continuously inject a cushion of microscopic air bubbles right along the forward keel. This bubble layer cushions the ship, cutting skin friction drag by up to 25%. But here's the clever engineering part. They place these vents strictly downstream, so absolutely zero air gets sucked into the propulsion intakes, which avoids any electrical disruption. Combine this bubble cushion with bio-grown shark skin riblets, and the total drag drops so much that this massive beast can sprint at 47 knots.
Which brings us right to Section 3, solid-state MHD propulsion, the silent, zero-friction engine room.
Heading inside the vessel, we find an engine room that basically throws out all the rules. Standard ships rely on massive marine diesels, loud, clunky shafts, pistons, and propellers that create crazy cavitation noise and require a huge crew of 25 or more just to keep running. The Lorentz Horizon replaces all of that with a supercharged maglev-coupled MHD drive. We're talking solid-state Lorentz ducts with zero moving thruster parts. It pulls seawater through using electromagnetic fields, giving it near-zero acoustic noise and completely silent fluid flow. Plus, the tech crew requirement drops down to just 10 or 12 people.
So how exactly does this work? It all comes down to the modular maglev cassette. Picture a hermetically sealed pure aluminum cell. Inside, a neodymium magnetic disc is literally floating in a viscous ionic liquid. External stator coils levitate and spin this disc mid-fluid. The takeaway here is that they can draw high-density power with absolutely zero mechanical touchpoints. No bearings, no friction, no wear and tear. It's brilliant. And because it's purely electromagnetic, it can do things normal ships just can't, like instantaneous 360-degree thrust vectoring. Imagine the Lorentz Horizon sprinting at 42 knots into a debris-filled disaster zone. Suddenly an obstacle pops up. A normal ship would suffer a grueling 30 to 60 seconds of mechanical lag trying to reverse its gears. But this ship, it just flips its electrical polarity. In under 1.5 seconds, the fluid flow reverses, and it goes from full speed ahead to full reverse. That is a total game changer.
Of course, pulling a high-G tactical turn in a 4,200-ton vessel creates massive lateral forces that would normally snap a ship in half. To handle this, the ship uses an automated liquid ballast network that shifts fluid in milliseconds to counter those heavy G-forces. And remember that living mycelium hull? Its structural scaffolding naturally absorbs and dissipates the shear stress. Add in the transverse MHD ducts, and the ship can actually crab directly sideways. The agility and tight spaces is just unbelievable.
All right, heading up from the hull to the top deck, we hit Section 4, Towers, Tech, and Drones, the Nerves and Wings. Dominating the profile of this ship are these massive dual 40-foot aerostator towers. Now these are 3-tier vertical axis wind turbines, or VOTs. They're designed to optimize vertical wind shear, giving a huge kinetic power boost at the top tier to harvest energy. But get this, they aren't just for harvesting power. The exhaust stators actually vector the wind to give the ship forward fluidic thrust, and they can actively assist the MHD steering during those sharp tactical turns. They're essentially rigid sails and power plants rolled into one. And since they eliminated the bulky traditional engine room, the whole top deck is freed up. You've got an automated carousel flight deck handling 20 VTOLs, and an insanely dense sensor canopy. We're talking drone-elevated ELF wire antennas and dual-tower ASA radar for high-def Doppler tracking. But the crown jewel is the multi-beam synthetic aperture sonar. Because the solid-state MHD drive makes basically zero acoustic noise, there's no loud engine rumble drowning out the signals. As a result, the sonar clarity is absolutely unprecedented.
Let's zoom out and look at the big picture. Section 5. The fleet's economic edge, outpacing and outmaneuvering the competition.
When you stack this up economically and tactically against existing naval fleets, the market dominance is pretty undeniable. For a hardware build of roughly $136 million, the Bio-MHD relief vessel gives you 4,200 tons of displacement going 42 knots in total silence. Look at the Spearhead class EPF right below it. It costs way more at around $180 million, but you're only getting roughly half the displacement, and you're dealing with loud diesels and heavy mechanical wear. The Lorentz Horizon gives you nearly double the ship for tens of millions less, completely outclassing things like the Daman OPV or the SAR Corvette.
And just look at the reaction times on this chart. Going from full speed to full reverse, the Bio-MHD vessel executes this in 1.5 seconds flat. Standard mechanical ships like the Spearhead or Daman take a grueling 45 seconds to pull that off. It just goes to show, absolutely no large displacement ship bound by mechanical drives can even come close to the high G agility of a solid-state electrical vessel.
It all boils down to this core philosophy. By stripping out traditional engine rooms, gearboxes, and massive flight deck crews, both construction and operational costs plummet. By abandoning moving parts and friction, the engineers unlock a self-repairing, ultra-fast relief node that drastically cuts down overhead. The ship essentially pays for itself simply by not breaking down the way legacy marine assets constantly do.
So considering everything we've just covered, the self-healing mycelium hulls, the silent magnetic drives, the instant thrust vectoring, are bio-grown solid-state ships the inevitable future of naval architecture? Can standard destructive marine diesels with all their friction and acoustic noise even hope to compete in the long run? It's a massive shift in how we engineer for the oceans, and it completely redefines what a ship can be. Let that sink in.